This is my DIY milling machine, and recently it's been working great, but I've had some backlash and I've been trying to figure out why. I used this milling table that I bought from eBay, which was originally lead screws, but I converted it to ball screws, so it's the X and Y axis, and surprisingly it still had backlash. I mounted my dial indicator here onto the end of the ball screw shaft, and as I jogged the machine in the Y-axis, the whole shaft seems to be moving in and out. And the same thing was happening on the Z-axis, so the ball screw would have to turn quite a lot before any movement was registered on the actual Z-axis. And that's nearly a whole millimeter. So I decided to look in the bearing blocks, and after taking the end plate off, which I thought maybe wasn't preloaded properly, I found just a couple of 6001 series deep groove ball bearings with no pre-tensioning and quite a lot of play in the ball bearings, which was really surprising because the machine hasn't been used that much at all. So I've made a little rig here demonstrating a deep groove ball bearing just to show what sort of effect is happening here when we apply a thrust load. This ball bearing has got inner and outer races where the groove is kind of symmetrical to this axis here. So it's just a simple groove in the middle of the race, and the balls are sort of trapped in that race. The balls, they have actually got spaces in between them, and there is a sort of a cage that separates them apart. This is needed because of the assembly process, so if you had no gaps you actually wouldn't be able to assemble this bearing at all. So because they push the inner race to one side and add the ball bearings on the other side, which is larger, it then allows full complete assembly. And the problem with this is when you apply a thrust load to it, the actual contact patch is very small. As you can see here, that ball is clipping here through the geometry, so that is the contact patch in this axis. And obviously on the other side of the ball it's the same, so it's this shoulder that's taking the load and this shoulder here. That's not a lot of surface area in contact. This actually allows the race to compress slightly and the ball to compress slightly, and also it allows the balls actually to slightly deform the cage and move side to side, which isn't ideal. So in the case of our double ball bearing bearing block, we have a second ball bearing here, and literally the same thing happens when you apply a load in one direction. Both the inner races move in the same direction, and the only thing that is beneficial here because of that second ball bearing is the force. The deflection is basically halved, isn't it? Because the force the force allowance is increased before you see a measurable effect. So it's kind of just like, you know, safety by numbers, really, that kind of approach. It's not ideal, especially in high load scenarios. So what we need to do is we need to actually separate those ball bearings slightly. So we need to move them apart slightly. So we would place the second ball bearing with a slight gap, or we would then add a spacer in between them, and we would then preload them against each other. So we would compress one race one way and the other race the other way. This puts the ball bearings in permanent sort of tension, in permanent contact. This kind of buys us more thrust capacity, I guess, thrust load capacity before we see a deflection. So as you can see, these are, you know, compressed. Now the problem with doing that is these ball bearings will wear out eventually because the contact patch is really small. As you can see, the clipping areas here, that's the only part of the ball that's making contact, so you're putting a lot of force on that part, and as the ball rotates, you know, it's going to either wear off this part of the ball, wear the shoulder out, and it will eventually just remain that shape. So kind of the real solution in a heavy axial load scenario is to use a angular contact bearing. That's what an angular contact bearing looks like. So as you can see, the race design is slightly different. So they are directional. So this one, if you apply the force this way, that inner race will just pop out and all the bearings will fall out. However, if you apply a force in the other direction, there is a lot more contact surface between the ball and the race, and also there are actually a lot more balls because they can be assembled just by adding the balls to the outer race and then putting the inner race in. So you don't need spaces in between them, so there are actually more balls taking up that load, so the longevity is increased. Obviously the problem is that you need pairs of them, but we already have space for two, so we put them in pairs. We rotate the second one 180 degrees, sort of like this, and we add that preload. So this thrust load capacity is now way more than the simple deep groove ball bearings, and we can't actually push the shaft out in either direction because they are working against each other. And obviously we add the little spacer in here. So that is what I did. So I bought a set of these fairly cheap but fairly high precision enduro bearings. They're supposed to be for mountain bikes, but it's gonna be fine. 7001 series RS, so rubber shields. And the only thing left to do was to figure out how to make a spacer or shim to sit in between them. I found a piece of scrap aluminium I had lying around the workshop from another project, and it's just under a millimeter thick. I think maybe 0.8 or something. It's not an exact science, but I decided to give it a go, so I just drilled a hole in the middle with a hole saw. That's just for clearing the shields and the inner race, and then the outer diameter I manually trimmed with some scissors because it was thin enough to be cut by hand. Cue assembly montage. Angular contact bearings go in facing each other, so blue seals facing each other. Tap them into place, tighten the end plate, added the retaining screw, added the timing pulley, used some vice grips just to get as much torque onto that retaining nut as possible, and then zero play. After all that work, I was really excited to get going, and I totally forgot to get any after measurements, but there was no play that I could detect, and I built a flood cooling enclosure for it next, and I did a whole load of test cuts. So I'm really happy with the result, and I hope that this video was useful to you in troubleshooting your own machines. If it was, drop me a like. Thanks for watching.